All right, welcome back to our third lesson on trigonometry. Today what we're going to do is we're going to look at solving for all angles when we're given a known trig ratio. So it's going to seem very disjoint, especially at the beginning as we're going through. If you feel like you're a little bit lost, and normally I would say stop and kind of rewatch and think over again, but in this case, I'm going to say like let's push through to the end because by the end we're going to kind of pull all these ideas together to get our final answers. And it's going to make the beginning part a little less important. So the first thing I want to do is take a look at something called basically the standard position of a graph. So far trigonometry has been all about triangles, and it turns out that we can also do it with basically any angle in a circle. Here we have let me just zoom in a little bit. Ooh, it's jumping all over the place. Here we have basically a coordinate axis, an x and a y, and we can think of an angle as being put here. We'll call that angle theta, and we're always going to measure that angle basically counterclockwise. So just for those who don't recall, clocks go this way, that's clockwise, and counterclockwise is the opposite direction to the way clocks go. So we're always going to measure counterclockwise from the positive x-axis, and when we reach the positive y-axis, that'll be 90 degrees, and by the time we get around to the negative x-axis, that's a 180 degree turn, and then we go to 270 and so on. Okay, so positive rotation takes us to positive angles, and similarly, a negative rotation takes us to negative angles. Make sense? If not, like I said, we'll keep going and hopefully it'll all kind of pull together as we go. So we're going to start with something called a unit circle, and it's in the Cartesian plane. And actually, sorry, I say unit circle except that I'm going to actually make it a circle of radius r. So if we take a look at our little triangle here, the triangle that we've been doing for the last couple lessons, that's what trigonometry is about, right? Oops. This triangle. I'm inscribing that triangle in the part of a circle so that basically I call this point up here where it touches the circle some random point P, and it has coordinates x and y. And then for my angle theta, you'll notice that this part here would be the adjacent, but it's also the x coordinate of that point xy. And likewise, this up here would be the opposite, or the y value of that coordinate. So for a circle of radius r, its opposite and adjacent are going to be its x and y values at that particular coordinate. So we can call the r the hypotenuse, and we can call the y value the opposite, and we can call the x value the adjacent. And in fact, the exact same diagram on the right-hand side there already has those three things listed on it. So what we're going to do from that is try to come up with basically some new equations or modifications of equations that we've already learned. So you'll remember that we did something called SOHCAHTOA. I'm just going to write that again here because why not? SOHCAHTOA. And in the old system, the sine ratio of an angle was the opposite over hypotenuse. The cosine was the adjacent over the hypotenuse. And the tan is the opposite over the adjacent. And in our new system, the sine ratio is basically the same thing. It's just instead of calling it opposite and hypotenuse, we're going to call that y and r. Makes sense? Similarly, our cosine with its adjacent over hypotenuse, adjacent is the x value over the r, and our tan opposite over adjacent is y over x. So the question is, why is this important? I'm just going to scroll back up to my original picture for a moment. And what I want you to see is you can define a point in the Cartesian plane in an xy plane without making a triangle at all, and you still can calculate a sine, cosine, and tan for our theta we don't actually need to complete a triangle in order for a theta to exist. It's just an angle in the coordinate plane between two lines. All right, let's keep going. Again, if you're a little bit confused, we're gonna get to the good stuff sooner or later, and then hopefully it'll all kind of come together. All right, so the quadrants. When we have an XY axis, a Cartesian axis, we break it up into 4 quadrants. Now, I've got a diagram here on the right that I pulled off of the internet. There's one little thing that I don't know if I should say change, but whatever we call them, I'm going to verbally refer to them as quadrants 1, 2, 3, and 4. Normally, they are listed, though, with Roman numerals. So that's quadrant 1, quadrant 2, quadrant 3, and quadrant 4, which is IV. Whether you use Roman numerals or numbers doesn't really matter to me. It's just a standard notation that most mathematicians use would be the Roman numerals. So again, these are assuming that we're starting at the positive x-axis and going around counterclockwise, which is, again, how we measure the angles. So we start in quadrant 1, and then as the angle gets bigger, it would move into quadrant 2, 3, and 4. And if it gets big enough, it goes back into quadrant 1. Okay, so quadrant 1 is going to make up any of the angles between 0 and 90. Quadrant 2 is going to be any angles between 90 and 180. And by the way, if they're exactly 0, 90, or 180, they're not really in any quadrant. They're just kind of their own thing. But we don't have to really deal with that. Then third quadrant is 180 up to 270. And fourth quadrant is 270 up to 360. And then again, once we get over 360 degrees, we're really back in quadrant 1. It's just we've done a full lap of the graph. Now in quadrant 1, x has a positive value, meaning that the x basically is over here, and likewise y also has a positive value. In the second quadrant, x is negative, but y is still positive. In the third quadrant, x is negative and y is negative. And in the fourth quadrant, x is positive and y is negative. So you'll notice that no two quadrants have the same pair of signs in that order. We have positive, positive, negative, positive, negative, negative, and positive, negative. And if we take a look at our sine, cosine, tan ratios, the sine ratio of any angle, theta, is y over r. And if we do that, keeping in mind that r is a radius, so it'll always be positive, basically it's going to be the same sign as y. So the sine will be positive in the first quadrant. The cos is x over r. R is positive because it's a radius. X is also positive, so it will be positive. And y over x is also positive. Moving into the second quadrant, y over r will be positive because y is positive. Cos will be negative because x is negative. And tan will be negative because y is positive and x is negative. So we'll have a positive number over a negative number. Continuing this pattern, in quadrant 3, y is negative, x is negative. Tan is y over x, so negative over negative is positive. And in the fourth quadrant, y is negative, x is positive, and then tan will be negative because we have a negative divided by a positive. Okay, now, if you may have heard of this last year, depending on, again, which course you took and who your teacher was, but something called the cast rule. And the cast rule basically is just a shortcut of this huge diagram we just filled in, and it says which of the values, which of the trig ratios, are positive in each of the each of the 4 quadrants. So this stands actually the A. Oh, sorry, I should point out the cast. We start labeling down here and call it CAST. There's nothing really to do there besides memorize that that's the order of it, starting in 4th quadrant, then going counterclockwise. But ultimately, once you memorize that, what this stands for is all sine, tan, and cos. Now, again, in quadrant 1 here, all three trig ratios are positive. In quadrant 2, only the sine ratio is positive. In quadrant 3, only the tan ratio is positive. And in quadrant 4, only the cos ratio is positive. So the CAST rule is an easy way to remember all that other stuff. This is just which trig ratios are positive in each quadrant. And this may seem like it's not that important, and you could argue that it's not, but we're going to use it in a second to actually solve real problems, at least real fictitious trig problems. Okay, so here's what we got. We've got 4 angles here. And what I'm going to do is just get you to use your calculator and fill in the rest of this table. So in the top left there, I'm going to get you to punch in the the sine of 20. So the sine of 20, and we'll do it to 4 decimal places just so you can see how this works. So this is 0.3420. And then what I'll get you to do is pause the video and fill in the rest of this table. And then when you're done, you can come back and check it, and we'll see if you see a pattern. One of the reasons I want to make you do this by yourself instead of just writing down the answers is if you do it, I think you'll more clearly remember the pattern. So anyway, pause it, fill in the rest of the table, and see what you get. Okay, so there are the values that you've got. And I hope you've made a couple of observations. So the first observation that I want you to make is that whether you're looking at sine, cos, or tan, all 4 of those angles have essentially the same value for the same trig ratio. All the sines are essentially the same, with the exception that 2 of them are negative and 2 of them are positive. And likewise, we have a different number for cos of those 4 angles, but they're all the same cosine value, except that 2 of them are positive and 2 are negative. And likewise, tangent, 2 of them are positive, 2 are negative, but the numerical value is all the same. So here's the observation. This first angle here, 20 degrees, that's in the first quadrant. And if we think about our CAST rule, I'm going to try and shrink this down just enough that we can get it on the screen all at once. Our CAST rule says in the first quadrant, all of our trig ratios are positive. And it says in the second quadrant, only the sine ratio should be positive. It says in the third quadrant, only the tan ratio should be positive. And in the fourth quadrant, only the cos ratio should be positive. So it turns out that both sine of 20 and sine of 160, let me get rid of the excess highlighting. Sine of 20 and sine of 160 have the exact same values. So here's a trick. If you're ever given sine of theta equals 0.3420, there's actually 2 answers to the problem. It could be 20 degrees, or it could be 160 degrees. And the whole point of this lesson is to be able to find not just the value that the calculator gives us, but that second value that's there too. Now, what I want you to notice about all 4 of these angles that I gave you, the 20, 160, 200, and 340, is that they're not coincidental. They're not just random 4 angles. The first one is 20 degrees. That's 20 degrees measured counterclockwise from the positive x-axis. The second one, 160 degrees, is actually the same thing. It's 20 degrees, but it's measured 20 degrees clockwise from the negative x-axis. This one here is 20 degrees there. I'm not going to worry about where they're coming from, but I think you can see that the size of each of these angles is 20 degrees. And likewise, this one here would be 20 degrees. 20 degrees backwards is the same thing as 340 degrees forward. All right. So this leads us to something called related acute angles. It's basically saying there's 4 angles that are essentially equivalent. They give the same numeric value regardless of which trig ratio you use. So if you choose to do cos of all four of those angles, you get the same numerical value, except that 2 will be positive and 2 will be negative, and that's determined by the cast rule. So I call it the bow tie diagram because I think it looks like a bow tie. But what it's saying is that whatever this angle is here, this angle, which is that angle backwards, or this angle, which is that angle above that, or, ooh, this is the messy one, that angle is the same thing as that angle. So all of those are going to be the same theta distance from the x-axis. It's just they're either above or below the positive or negative x-axis. Again, some of you are probably still thinking, what does this have to do with anything? I don't get it. Let's answer some questions. Okay, so let's say that we have an acute angle of 12. What that is, again, if I can get this all on the diagram at one time, or all on the screen at one time. Get rid of that extra stuff there. Okay. So what I want to do is find the 3 other angles that kind of match the first angle. So the first angle we're going to say is 12 degrees, and I'll be doing a lot of erasing on this diagram because it takes up a lot of space, but we're going to say that's 12 degrees. Well, if that's 12 degrees, the next related angle is going to be basically this line here, and it's going to be 180 minus 12. And 180 minus 12 is 168 degrees. And if you wanted to right now, you could pause the video and verify that the sine of 12 and the sine of 168 is exactly the same value, or you could just keep going and trust me with it. The third quadrant value is going to be 180 plus 12, and 180 plus 12 is 192 degrees. Now that's going to have the same numerical value, except because it's CAST, because it's in quadrant 3 where only tan is positive, the sine value in that quadrant would be negative. It'd be the same for a number like 0 point whatever, but it would be a negative version of it. And likewise, the fourth quadrant angle is going to be 360 minus the 12, so 348. Okay, so hopefully that's kind of making sense. These 4 angles basically make up the bow tie. They're all 12 degrees away from the x-axis, but we're always measuring their full values starting at the positive x-axis and kind of going all the way around. All right, again, I'm going to erase that because it's making a huge mess. And let's try the next one. So the first angle is 35 degrees. The second angle is 180 minus 35, so that's 145 degrees. The third related angle is 180 plus 35 is 215. And the last one is 360 minus 35, which is 325 degrees. And then finally, despite the fact I'm going to make the same arrows again, at least I find it a little easier to explain what I'm doing, even if the diagram is horribly inaccurate for the numbers we're using. If we pretend that this is 88 degrees, then this angle here would be 180 minus 88, which would be 92 degrees, which of course would both be much, much larger angles on the diagram, but it doesn't really matter. The third one would be 180 plus 88, which would be 268. And the final one would be 360 minus 88, which is 272, I believe. Okay, so given any acute angle, you should be able to find the 3 related angles. And it's basically just taking that angle and adding it or subtracting it to 180 or 360. And then, yeah, you're done from there. All right, so here's what we're going to do. We're going to use our calculator to find the sine, cos, and tan of our one angle here of 27 degrees. It's the one we're choosing to work with. We're going to do that one with a calculator, and then we're going to calculate the rest without a calculator. So the first one is sine of 27 degrees. And that gives me 0.4540. The cosine is 0.8910. And the tangent is 0.5095. Okay, so that we did with our calculators. Now what I want to do is find the three related angles and put in their sine, cosine, tan ratios, but without touching a calculator. Okay, so first of all, the second quadrant one is going to be the 180 minus 27. That's 153 degrees. The third one is going to be 180 plus 27. That's 207 degrees. And the last one, if you can picture it in your head, is 360 degrees minus 27 is 333 degrees. And if at any point it helps you to draw any of the diagrams we've done above, the bow tie or whatever, the cast rule, by all means, feel free to do so. In fact, before I do this next part, I think I'm going to do my cast diagram real quick down here. C-A-S-T. And now what I can do going back to my table is I realize that the sine value, 0.4540, is going to be the same number for all four angles because they're all related. The only difference is I have to check which ones are positive and which ones are negative. But according to the cast rule, everything's positive in the first quadrant, which is why we got three positive numbers. In the second quadrant, sine is positive. I normally wouldn't write the positive there, but let's just emphasize that those are positive in the first and second quadrant. And then in the third and fourth, only tan and cos are positive, so the sines are negatives. Similarly, all four are going to have the same cos values, except for the sine. And according to the cast rule, cos should be positive in the first quadrant and the fourth quadrant, and negative in the second and third. And then finally, the tangent of all four of those angles is going to be numerically the same. And we can see from the cast rule that tan will be positive in the A quadrant because everything's positive in all. And the third quadrant, it will be positive. So first and third are positive, meaning second and fourth are negative. Okay, I mentioned earlier, if you were kind of lost, that's okay. You can kind of be a little lost, but we're starting to get to the point where we're trying to pull this stuff together. So let's use our calculator to find a few things. First of all, we'll find the sine of 43 degrees. So the sine of 43 degrees, that one's easy. It should only have one answer. That's 0.6820. Similarly, cos of 71, that's in the first quadrant. It should be a positive number. Cos of 71 is 0.3256. There's only one answer to it. And finally, the tan of 12 degrees should be positive. It's in the first quadrant, and it is 0.2126. Okay, so we've been doing this for forever, punching angles in and getting a trig ratio out, basically a decimal number. Now what we're going to do is we're going to use our calculator to solve the following. So basically work backwards. And again, we've done this before. We did it in the last couple lessons. So what I do is in my calculator, I put in 0.3420 inverse sine, and it gives me 19.998. That's 20 degrees. So 20 degrees is what my calculator says. And then I have cos of theta equals 0.6157. So I put in 0.6157 inverse cos, and I get 51.99 or 52 degrees. And then for the tan, 0.293 inverse tan. And let me just double check that one. 2493 inverse tan. 13.99, about 14 degrees. Okay, so we've been doing that for a while too. The entire point of this lesson, though, is that that's actually not the only possible answers. That's the calculator answers, and the calculator will always give us the acute angle, the small angle, almost always the positive angle. So 20, 52, and 14 degrees are answers to those questions, but they're not the only answers to the questions. So here's what we have to do. You'll notice that question 6 has basically the exact same question again. It says sine of theta equals 0.3420. The only thing that's changed is it's asking us to find all of the possible answers between 0 and 360. So what I'm going to do for my first diagram for this one, I'm going to put down theta equals 20 degrees, but there's going to be a second one. How do I find the second one? Well, I start off by writing down cast. And I know one of the angles is 20 degrees, right there. And I know that the other place where sine theta will be positive is in the second quadrant, which means it's going to be 20 degrees here. Unfortunately, 20 degrees in the second quadrant is not the other answer. The other answer is the equivalent one measured from here, which is 180 minus 20. And 180 minus 20 is 160 degrees. And if you pull out your calculator and you type in inverse sine of 160 degrees, you will see, inverse, let me try that again, regular sine of 160 degrees, you'll get out 0.3420, which also is another answer to that equation. So there's two possible thetas that will work. In theory, there's an infinite number of thetas that will work, but I put a restriction on it. We're only looking between 0 and 360 degrees. If we went around the circle an entire time and then a bit more, so we did this, that would be 380 degrees, and 380 degrees would also give a sine, or sine of 380 would also be 0.3420. So there's a whole bunch of angles that work, but there'll only ever be two between 0 and 360. Okay, let's try this next one. Same idea. We know that from the question above, 52 degrees is one of the angle. That's here. But if I put cast on there, I know that I'm also going to get a positive cos value in the fourth quadrant. So I'm going to have a related angle here, which is 52 degrees. But that's 52 degrees backwards from 360. So 360 minus 52 is 308 degrees. And 308 degrees is our second answer to that one. Finally, tan of theta equals 0.2493. We know that one of the answers is 14 degrees. Right there. But I also know because of cast rule that there'll be another positive tan answer in the third quadrant. And that's going to be 14 degrees below there, which is 180 plus 14. So 194 degrees is another possible answer to that question. And likewise, you could keep going with going around the circle over and over and over again to get more angles, but we're only going to do between 0 and 360. Okay, so hopefully this is starting to pull together. Everything we've done up to this point is basically so that we can say we know how to find that second angle that makes the trig ratio true. So let's try this one and see what happens. It's going to be similar but not identical. So the first angle we're going to get in our calculator. So I'm going to put in, this is the first time I think we've ever done a negative ratio. We're going to put in negative 0.2756 inverse sine, and I get out negative 16 degrees. So that basically means I have this angle right here. And according to the cast rule, I have a negative sine ratio, which means it should be negative. It's going to be positive in the first and second quadrant. It's going to be negative in the third and fourths. So there should be another one over here that's also 16 degrees. Now, interestingly enough, the calculator value we got of negative 16 is not even one of our valid answers because it's not between 0 and 360. The two valid answers to our question are 180 plus 16, and 180 plus 16 is 196. And the second answer is going to be going all the way around, which is really the same thing as 340 minus 16, or 360 minus 16, which is 344. And if you want, you can always verify quickly and easily enough that the sine of 196 is negative 0.2756, and the sine of 344 is negative 0.2756. Let's try that again with the cos version. We already have cos of theta. We can use our calculator to find out that negative 0.3907 inverse cos is going to give us 113 degrees. Now that is a valid answer. And 113 degrees is just over 90, so it's going to be over here. But that means that this angle here is going to be 180 minus 113, so that's going to be 67 degrees. Cast says that we're going to be positive in the first quadrant, negative in the second quadrant, which makes sense because our negative cos did give us a second quadrant answer, so we'll be negative there. It's going to be negative in this quadrant, and cos will be positive in the last quadrant. So we want the second and third quadrant versions, which means that we want basically 180 minus 67, which is the one the calculator gave us, and 180 plus 67, which gives us 247 degrees. All right, the tan one. Here we have a positive tan, 4.3315. Second function tan. And the answer to that, at least one of the answers, is 77 degrees. So that's going to be something like here. And I'm going to put cast on there again. And this time tan is positive, so that should be in the quadrant where everything is positive and in the third quadrant. And if we have 77 up there, the other one should be 77 down there, which is really 180 plus 77. And 180 plus 77 is 257 degrees. Should be our second answer. And again, you can punch it in and find out. The tan of 257 is 4.3315. Yeah, perfect. Okay, so we're there. Basically, everything we did led to the cast rule, the idea that some quadrants have positive trig ratios, some have negative, and they let us find out where our answers should lie so we can calculate them using the related acute angles from the bow tie diagram. That was a mouthful. Okay, let's try one more little problem, and then we'll let you try the practice problems to see if you're getting this. Okay, so we're given that cos of theta equals negative 0.3907. So theta, I'll just punch that into my calculator. Negative 0.3907 inverse cos gives me 113 degrees. But I'm also told that theta is in the third quadrant, and I think we can see from this that theta is not in the third quadrant, at least that answer is not. So here's 113 degrees. But if that's 113, it means that this one's 67. And CAST means we're going to have another negative value here when that's 67. And that value is going to be 180 plus 67. 180 plus 67 is 247, I believe. And I'll just double check that one. The cos of 247 degrees is in fact negative 0.3907. So that's the one that works. So now I'm going to just cross this out because that's not one of the, that's one of the possible answers for theta, but it's not the one that's in the third quadrant. So we know theta is in the third quadrant. And we want to determine the values of sine and tan. So this shouldn't be too hard now. We just do the sine of 247 and the cos of 247. And just before I do that, I'm going to look at this and say, wait, they're in the third quadrant. According to my CAST rule, the third quadrant, only tan is positive. Oh, sorry. I put down cos up there, and I meant to write tan. Sine and tan. So I'm expecting a negative answer for my sine and a positive answer for my tan. So we'll try sine of 247, and that gives us negative 0.9205. As again, we suspected it would be negative. And the tan of 247, which is expected to be positive and is, it's 2.3558, or 2.3559, I guess, rounding off properly. Okay, so just to summarize what we've been spending this entire time doing, and it's basically just working up to the idea that trig ratios don't have to specifically refer to triangles. They can refer to any time you've got an angle in anything. In this case, we're just doing angles around a circle. And we want to be able to solve for all possible answers, not just the acute angles, like we have been up to this point. And we have been up to this point because we've only been doing right-angled triangles, and right-angled triangles never have any angles over 90. So nothing we do would ever give an answer in the second, third, or fourth quadrants. But in many of the situations, like the ones we're going to be getting into in the next few lessons, we may have angles that go into the second quadrant, and we need to understand that there may be more than one answer to the problem. Anyway, I'm going to stop there. You try the practice problems. If they go well, fantastic. If you're struggling, I'd ask that specifically in this one, you go back over the lesson a little bit more and just see if you can get it from doing the diagrams again. Drawing the diagrams in this is a big help, and writing out the CAST rule, the CAST on your graphs, is a big help as well. If you're still stuck, reach out, ask me for some help, and I'll see what I can do. Okay, good luck, and I will see you in the next lesson.